Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And for the last few lectures, I've been talking about functions, which is in section 5.5 of Volume 1. This is my fourth lesson on functions. Today I'm going to talk about composition of functions. So, anyway, let's begin. So, what do we mean by composition? Well, suppose we have two functions, say f going from x to y, where x and y are sets, and g going from y to z. And then we say the composition of f and g, which we write, this is a little bit confusing notation. When we compose functions, we actually write them backwards. We write them in reverse order. So the composition of f with g we would write as g of f. This is a little hollow circle in the middle, g hollow circle f. That's just so g circle f of x would be just be g of f of x. So first we apply f to x, and then we apply g to f of x. So you can see the way we write functions, we always write the name of the function to the left of the argument. That's why we have to keep proceeding to the left. Well, I guess that's a little bit of an unfortunate consequence of functional notation. Maybe it would have been better to put the name of the function to the right of the argument. I don't know. But that's the way we do it. So and you should note that in general we can compose functions. Sometimes we can compose functions both ways. It depends on what the sets are. But sometimes we can do both f of g and g of f. In particular, if the domain and range are the same sets, we can always do that. But anyway, I'm just going to do, and then the thing I wanted to say is that in general, f of g is not the same as g of f. It depends on the order in which we compose functions. So now I'm just going to do a couple examples. So for the first example, let me switch to the next slide. Let's consider the functions f, and these are both functions from the real numbers to itself. So we're going to define f of x to be 2x plus 1 and g of x to be 3x plus 1. These are both simple linear functions. And now we were asked to compute what f of g of x is and g of f of x. Well, I think it's pretty straightforward. Let's do f of g first. So f circle g of x is just f composed with g composed with x. So the first thing, and we always don't want to do the inside of the parentheses first. So f is a function. F of x is 2x plus 1. Therefore, f of g of x is 2g of x plus 1. We actually go from the outside in. And then we plug in what g of x is. So g of x is 3x plus 1. So now we're going to get 2 times 3x plus 1, in parentheses, plus 1. 2 times 3x plus 1, this is just simple algebra. 6x plus 2 plus 1, that's 6x plus 3. So that's what f of g is as a function, 6x plus 3. But now let's go the other way. So if you go the other way, I'm not going to go through every step again, but it turns out you get something different. You get 6x plus 4. So in this case, indeed, f of g and g of f are different. But now let's do another example. Let's say, again, f of g are both functions from the real numbers to itself. And let's say f of x is 2x plus 1 like it was before, but now g of x is 3x plus 2. Well, if it turns out, if you work out what f of g and g of f are, in this case they are equal. They're both 6x plus 5, and you can check for yourself if that's the case. So sometimes they're equal, but most of the time they're not. This is kind of an unusual example. So that's composition of functions. I think you get the idea. And you can do it as many times as you want. And not only can you compose functions ad nauseum, but you can compose, if a function has the same domain and range, you can compose a function with itself. So, so when you do that, I mean, the way the notation people use for composing a function with itself, I think I have to go to this slide here, is they write f sub. We put a little superscript with a parentheses above it, indicating the number of times we're composing the function with itself. So, for instance, f superscript 1 in parentheses of x, that's not very interesting. That just means we're composing it once. That's just f of x. We're applying it once. And if you applied it twice, you would have f of x. That would be f superscript 2 in parentheses x. F superscript 3 in parentheses x would be f of x. I think you get the idea. This is a recursive procedure. So in general, f superscript fn of x is f of f superscript n minus 1 of x. Another way to say that is f superscript n is f circle f superscript n minus 1. That's kind of a recursive way you can define, self-composition, an arbitrary positive number of times. And I think you can convince yourself, it's not too hard to show, that if you compose a function with itself m plus n times, that's just the composition of the function composed with itself m times, and the composition of the function composed n times. So composition is a little like multiplication. It's a type of it's actually a type of group multiplication. I'm going to talk about groups in chapter 6, but this is a group operation, it turns out. But we could also, remember I talked about inverses? So if we compose a function with its inverse, I think that's how we define the inverse. If we compose a function f with f inverse, it doesn't matter which order you do it, f circle f inverse or f inverse circle f, both of those are equal to the identity. Remember, the identity is the function that doesn't do anything. That's also f superscript 0 of x. So when you compose a function with itself 0 times, you just get the identity. Basically, these four equations, 5.5.1 through 5.5.4, on the bottom of the slide, these show you all the rules for composing functions with itself. And you can see they work just like exponents. And the reason they do is, like I said, this is a type of group multiplication. But, if you don't like that, you can just memorize these rules, which aren't hard to memorize. The last rule says if you compose a function m times n times, that's the same as starting with a function composed m times and now composing that new function n times. And here's a couple examples. And then, next slide. I give a couple examples. So suppose we have the function again, or actually this is a different function. Suppose we have a function for the real numbers to itself defined by f of x equals 2x minus 1. Now we're asked to compute f superscript 2 of x. That's just f of x, if you like. And also f superscript 3 of x, which is f of x. So let's do that. So f superscript 2 of x, like I said, is f of x. Well, that's 2f of x minus 1, or 2 times 2x minus 1. In parentheses minus 1, if you work that out, you get 4x minus 3. And then if you did it another time, you can use the recursive definition. F superscript 3 of x is f of f superscript 2 of x. We already calculated f superscript 2 of x. That was 4x minus 3. And when you do the math, you'll find that f superscript 3 of x is 8x minus 7. So that's a simple example of composing a function with itself. And that completes my video for today on composition of functions. So thank you for watching. Long live math, and I'll see you guys next time. Bye.